Hello everyone, welcome to a session on learning glass. We're going to do a little bit more lecture stuff on this recorded video. So today we'll talk about adiabatic process for an ideal gas with constant heat capacity. So adiabatic means that there's no heat transfer during a process. So you do a change of your energy of your system and there's no Q, which is heat in our symbology. And this can be expansion or compression. So adiabatic expansion or adiabatic compression. Adiabatic just means no heat transfer, but we're going to do an analysis for adiabatic expansion or compression of a closed system. So expansion or compression of a closed system without heat transfer is what we're going to do now. So it's a closed system, and we're trying to understand this from a thermodynamics perspective. So we're going to use the first law of thermodynamics for this particular case. So for a closed system, the first law, closed system without chemical reactions, the most straightforward form of the first law is to express the internal energy in terms of U, not H. We'll talk about this in class or other videos, but for this particular case, we'll start with the first law in this form. The differential change in internal energy U is balanced by some infinitesimal energy transfer by heat and some infinitesimal energy transfer by work. So the nature of these two properties are, this is what the system has before and after a process. This is something that happens in between. So mathematically, this is a state variable that it's only related to the properties of the system. This are actually properties of the process. And the reason why they have these different squiggly lines is because it matters which pathway you take here. It does not matter which pathway you take here. We'll talk about more of that in class. But this is the one way to write the first law. U, because it's a closed, unreacting system, and this infinitesimal, these calculus type form is so that we can understand this from, by taking the integrals. It'll also come out to deltas and Q's, as we'll see soon. But since we're talking today about an adiabatic system, there's not going to be any heat transfer. That goes to zero, so what's left over on the first law is that this infinitesimal change in internal energy is balanced by the work that goes through. So next step is we'll start to evaluate this internal energy and this work transfers. So those two will use the definition of heat capacity at constant volume. That by definition is related to CV, or like the CV is tied to U, internal energy. And when you rearrange that for all processes, you can say that the change of internal energy is related to CV and a change in temperature. And for work, it's a mechanical thing, so it's by definition some force over a distance. And then when we relate it to pressure and temperature, you can write it as pressure times a change in volume. And so we'll use those and plug them into our first law of thermodynamics. And what that would give us is that on the left-hand side, plug that in, and then you'll get then, if you use the ideal gas equation, as we said here in our assumptions, this is an ideal gas. We have P times small v equals RT, or P big V equals MRT, or another way of saying the ideal gas, big V equals NRUT, where this is universal, and this is moles. So little v means volume per gram. And we'll continue with this form. That's what this is, small w, small v. Pressure is always extensive, but we'll move forward with that form. So I guess this is a good time to start making more space. Let's erase some of this stuff. Okay, let's go from here. So we'll plug in the ideal gas equation. So that would give us CV negative RT dV over V. Then we can bring the t on this side. So that'll give us two integrals, a separable differential equation. Meaning that the left-hand side has one type of variable, the right-hand side has another type of variable, assuming constant heat capacities. R is a constant. So we have this separable differential equation, and it's a relatively simple one. We can just do this integration, which would be the natural log. So that's how that integral would work out. Then if we rearrange things, we end up with a natural log. So then if we take the exponent of both sides, or if you have natural logs on both sides, skipping a few steps, we'll bring this constants on one side and then cancel out the natural logs, or constants on one side, then bring that to the exponent as the natural laws allow you to do. And after skipping a few steps, you would end up with these ratios, T1 to T2. And these come in the exponent from the natural log. It's on the multiplied a natural log. You can put that inside as an exponent, algebra 2 type stuff. So that's how that would cancel out. And what you would see is a relationship. So this is the solution of this differential equation. It's the first law of thermodynamics. You plug in the ideal gas equation. You, without any heat transfer, you get this relationship here. And so what happens is, this is what the relationship you get. And for constant heat capacity and adiabatic, this is what you get. And the only way that this can be possible is as if this is a constant value. So what this relationship tells you is that there's some, these relationships pop out. So first off, for constant heat capacity, as we say here, but also if you define this parameter K to be the relationship between your heat capacities, Cp and Cv, what this shows is that just any temperature at one state times the volume at one state raised to this equals constant. I guess I ran out of space there. Let me write it over here. So T times the volume times K minus 1 raised to the K minus 1 equals constant. But if you use the ideal gas equation, you can relate P's and T's and V's, and you can also show that P times V raised to the K equals constant, and T times P times raised to this exponent equals constant. So depending for an adiabatic process, for an ideal gas, constant heat capacity, you can show that you get these relationships pop out from the first law of thermodynamics. And depending on which variables you have, these might be convenient. So like we said here, you can this Cv and R become K because for ideal gas, we won't talk about how this happens, but this is one property of ideal gas. The Cp is related to the ideal gas constant by that Cv plus R adds up to the Cp. That's where you can get this relationship between R and Cv's. Then depending on which variable you have, you can get these relationships out. Okay? So we can start using this. Let's start using this to evaluate work. So we said that work is the force over a distance. It can be related to the pressure over a volume, exerted over a volume change. And we can also use the ideal gas to get more details on how to quantify this work transfer during ideal gas. So the differential change in work, amount of work done, is equal to the pressure and the volume change. Then, if we use this relationship here, we can show, to plug this into pressure, we can show that P equals some constant times V to the negative K. So we solve for P here. Then we plug that back into the integral. So what you would get was that work equals the integral of this constant times V to the negative K dV. And if we remember from calculus class, this integral is relatively simple. Plugging that in, you can pull the constant out, and then you would also pull this exponent out. It becomes the denominator. What is this? Yeah, negative K plus 1. That's in the denominator, and then this exponent becomes negative K plus 1. Evaluated at V2 and V1. So that's this relatively simple integral. And of course, K is this ratio of heat capacities. This P comes from these isentropic or adiabatic relationships we found. then let's see how we can relate this more into these relationships here. Okay, so if we say that okay, let's expand this out. Let's say the work is the integral of this. We saw that the integral comes out to 1 minus k. Then v 2 1 minus k minus v1 1 minus k. That's what that integral is. Okay, let's use this relationship here. P1 V1 raised to the k equals P2 V2 raised to the k. Then when we plug that in, that's basically it. Yeah, so I guess I'll do is add one more step in there. Well, first let's let the c equal c. So if we choose this c to be P2 equals V2, we'll plug that in first. We'll say 1 here, and then c equals P2 V2 raised to the k times V2 1 minus k minus P2, oh, I'm sorry, no, I messed up here. This should give us, we can solve for P2 here. P2 equals P1 V1 over V2 raised to the k. Or, yeah, it depends on the way you do it. Let's go back to what I was doing before. If this equals c here, I can just say simply this. C comes to multiply to both of these, then I can just use c in both of these cases, P1, V1, k, and that's it. So at the end, the final result, you can play with this algebra in many ways, and but by just choosing c to be one of this here and c to be this here, you can get what I was looking for, which is at the end, the work of an isentropic adiabatic process. If you do this integral using all these relationships here, you would see that it just comes out to related to the pressures and volumes. So P2 V2 minus P1 V1 over 1 minus K. That's the work for an adiabatic process with constant heat capacities. And this all comes in from the first law of thermodynamics and the ideal gas equation. So what's embedded in here is the ideal gas equation and constant Cp and Cv. And if we go back to the first law, yeah, going back to the first law here, these and this. So for, I erased it, but the definition of heat capacity is that du equals CV dt for every process, but for constant heat capacity, you can say that the delta U equals CV delta T. That's what's happening in this case. And then if we showed this integral already, we said work is the integral of this, which would be this. That, by the first law of thermodynamics that's here, we basically can tie the way that this is constrained is that the change in temperature, I'll say T2 minus T1, is constrained by the work, by the first law. This is how they're both tied in. So that's another constraint on this analysis, is that if you were to expand or compress a closed gas, if by the ideal gas equation in the first law, that's how all of these are related. If you compress it, the pressure increases. The P1 is your starting pressure. If you compress it, the pressure will increase, the volume will decrease, and the actual quantitative relationship between all of them, the pressure, temperature, and the volume, is constrained by the first law of thermodynamics. And all these assumptions we made, this is how they're all constrained together. And so that's how this analysis would work out. And about the units, this is all, the way that we did it is this is per gram, per kilogram, let's say, per mass. This is, let's say, kilojoules per kilogram Kelvin. If you were to plug in the ideal gas equation in the other forms that we talk about, you can relate this to temperature as well. Like if you multiply this by mass, multiply both sides by mass, you would get m small cv delta T equals P2 times big. So this should be smaller. This should be the per mass. Let's trim this down here. Big volume, not per gram volume. And then you can relate it to temperature as well. Where you can say PV, big V equals M RT. And when you show, so if it, soon enough you'll see that it's basically the same equation. And I'll leave it for an exercise, but R over 1 minus K is the same thing as CV. So you're basically repeating this equation just because we kind of used all of these related equations over and over again. This is useful, but as soon as you start to express this in terms of temperature, you'll see that you're basically saying the same thing, because we use the ideal gas equation here. We plug this in to get temperatures on the right side, and then what you'll see is that CV is related to R over 1 minus K. So these are all just some considerations for this specific case of an adiabatic process. As we'll learn, this also means isentropic process because of this, how it's related to entropy, meaning delta S equals 0. But beyond that, we can constrain the compression or expansion of a closed system, the gas inside, by this relationship here, which is useful. And like for example, if a gas goes from a lower volume and you expand it, most gases will decrease in temperatures depending on the specific heat at constant volume. So with that, I'll go ahead and end this session, and I'll see you next time. Thank you.